We're now solving the master questions for this chapter, for lesson 3 on this chapter. The first one is question 10 from a paper, the paper 11, May-June 2012. It says, it is given that a curve has equation y equals f of x, where f of x equals x cubed minus 2x squared plus x. Find a set of values of x for which the gradient of the curve is less than 5. That's the first question. And then find the values of f of x at the 2 stationary points on the curve and determine the nature of each stationary point. 9 points for this question. And this should be answered, if you know what you're doing, this should be answered like in a few minutes, a couple of minutes. Let's see. So proving that, or showing the values of x for which the gradient of the curve is less than 5 means what? Means differentiating the function and testing it for any value that is smaller than 5. So differentiate this, and you have, it is a cubic, so you have this quadratic, and put it smaller than 5. Okay, this is the same thing as sending this to this side. Okay, and then what do I usually do in these cases? I solve this inequality as a quadratic, okay, and I equal it to 0 to find the coordinates of x for which it is 0. Okay, I did this by factorizing, and I got the values x equals 2 and minus 2/3. All right, okay. Then what do? I plot these points on a line at random positions, the negative first and then the positive 1. I look at the nature of this quadratic, namely the coefficient of x squared, and I know that is a parabola such as this one, where these are the stationary points, where these are the roots of the quadratic. Then I go back to what is being asked, and I want what? I want the negative portion of it, and the negative portion is where? Is in between the roots. So that's the final answer. Again, recapping, I make the derivative smaller than 5 as the question asks, put everything to one side, and I have an inequality. I stop here and I solve the equation, okay, the quadratic equation. I find the values of x for which it is 0. I plot them very quickly on a little sketch. I sketch the corresponding parabola. It's a positive parabola given the nature of, given the sign of the coefficient of x squared. Then, and only then, I go back to the inequality and I look to the portion that I want, is a negative portion in this case. The negative portion is found over here, which is my final answer. Okay, then the second question, find the values of x at the values of f of x at the 2 stationary points on the curve and determine the nature. So what is this? This basically is asking me to differentiate the function and equal it to 0. Okay, and solve it. That's what I did. And the x coordinates of the stationary points are 1/3 and 1. Then I find the corresponding y coordinates by substituting the values of x on the original function. So f of 1 for this and f of 1/3 for that. And here you have the corresponding values. So the points are 1, 0 and 1/3, 4/3. 4/27, that is. Then for the nature, just do the second derivative of this, substitute on its expression the values of x that you got before, see if they are positive or negative. If positive, minimum. If negative, maximum. So the first one is a minimum, the second one is a maximum, and write it down. This could be done, if you know what you're doing, this could be done in like 3 minutes. And with 3 minutes, you have already 9 points. Second question is spring 2015, paper 11, and it's question 9. The equation of a curve is y equals x cubed plus px squared, where p is a positive constant. First question is, show that the origin is a stationary point on the curve and find the coordinates of the other stationary point in terms of p. Find the nature of each of the stationary points. Then you have another curve with equation y equals x cubed plus px squared plus px, and find a set of values of p for which this curve has no stationary points. Okay, so then if you need to know the stationary points, namely proving that the origin is one of them, this is standard procedure again. Just get the derivative and equal it to 0. This is what you get. You have an expression in terms of p, okay? Factorize x and equal it to 0. So 1, as expected, one of the solutions is x equals 0, and the other one is an expression in terms of p that you equal to 0. And here you have the two possible solutions for the equation. Plug this here on the original function, and you have the corresponding y coordinate. So here you have the first point, which is 0, 0. And thus you prove that the origin is one of the solutions. Then plug this in on the original function, on the cubic function, simplify it, and here you have the coordinate, the y coordinate, in terms of p. Now, you need to know, look again, the coordinate of the other stationary points in terms of p you already found. Now, to find the nature of it, you have to differentiate it again, get a second derivative. Here you have it. And then plug on x the x coordinates of the stationary points. The first one is 0. The other one is this expression in terms of p. Plug it there. And you get this expression, minus 4p minus 4/3 of p. But then, and only then, you look at this tiny detail that you had over here. P is a positive constant, and this will allow you to find the nature of the second stationary point, because if this is a positive constant, whatever value that you plug over here, this is always going to be negative. And this proves that the second stationary point is a maximum. So first one is a minimum, because you have, by the way, I didn't tell this a little while ago, and it's the same kind of logic. You have an expression for the second derivative as being 2p when x equals 0. And again, if p is always positive, so this is also going to be always positive, which means that this is a minimum. Okay, so the first one is a minimum, the origin, and the second one, this point here in terms of p, is a maximum. Then find a set of values of p for which the curve has no stationary points. This is solved using what? A quadratic, right? You have a cubic, but if you differentiate it, then you have a quadratic. Okay, if you want no stationary points, then the discriminant needs to be negative. So here you have the quadratic. In terms of p, your b squared minus 4ac is going to be just this. You want it to be negative. So again, stop, and this is the way I solve it. I solve the corresponding quadratic equation, equaling it to 0. I get these two values of p. I sketch them very quickly on a line. Look at the quadratic that you get out of this discriminant. Okay, not that quadratic, but this one. It's a positive quadratic because the coefficient of p squared is a positive number. Sketch it down. Then I look back where I left it, the inequality, and I want the portion of this tiny quadratic that is negative, and it happens between 0 and 3, and that's my answer. There are no stationary points for any value of p between 0 and 3. Last question, last exam question is winter 2014, question paper 13. And the question itself is question 3. So express 9x squared minus 12x plus 5 in this form, in this completed square form, and then determine whether this cubic over here is an increasing function, a decreasing function, or neither. Apparently this doesn't have anything to do with that, but we're going to see that indeed it does. So the first one is just a completed square form question. Turn this into that. So open brackets, and you need to get the square root of 9, which is 3. So put 3x, half that. Sorry, let me see one thing. Okay. What is the number that multiplied by this times 2 equals minus 12? That's minus 2. Again, minus 2 times 3, that's minus 6, times 2 gives minus 12. So that's what you write over there. Then you mentally square this. Minus 2 squared is 4. So you remove it, or you just put minus 2 squared over here. Add the 5, and you'll end up with 1. Okay, so if you want to test it, just expand these brackets and you should get that. Then you want to determine that this is an increasing, a decreasing function, or neither. Okay, so what you do to solve this type of questions, differentiate it equal to 0. And no surprise, when you differentiate this, you get the original quadratic that you got on question 1. Equal it to 0, so you can use what you got on the previous question. Use a completed square form instead, it's much quicker. And you'll see that if you try, after sending the 1 to the other side, you have a negative number, then you are unable to solve this using any real number, okay? So this proves that you have no stationary points. Again, if you have no stationary points, this means that the function is either always increasing or always decreasing. Which one? Just test the gradient for any random point. So I picked 0 on the original function, and I got a positive number, meaning that this is an increasing function, always an increasing function. It doesn't ask you to sketch the graph, but if it would be something like, let me just sketch it very quickly over here. It would be something like this. It's a cubic, maybe something like this, always increasing, okay? Actually, you have no stationary points. Yeah, so you wouldn't even have that. Never mind this bit. There's a reason why I didn't write it in the first place. It really doesn't matter the shape. You just need to know that it is always an increasing function because you have no stationary points, and the gradient of any point is a positive gradient.